Y'all flew last week. Do we have any questions about that? All the data turned out just great.
Still don't have all the data.
Okay, yeah, we'll need to do some data exchange probably at some point here so we can actually come up with position corrections for the airplane. And I've got a reasonable idea of what those ought to be from past classes, okay? So, and we're going to use this, one of the reasons, of course, to do airspeed calibration first is that you're going to use that data for the rest of the class. Okay? You know, we're going to use it to correct other data that we get as we go along. So that's why it's pretty important. And if it doesn't turn out right, well, like I say, I'll dredge up some data from a past class who did and hand it off to you if it doesn't look too good. But anyway, that's what we'll do. Next week, we're going to do stalls. Okay, we'll do both clean, gear down, flaps up, power off stalls. Now, the FAA allows you to do them in two separate ways. One, power off or power idle. And the other way is they'll allow you to do zero thrust. And generally zero thrust will be a little slower than power off. The reason for that is that the up elevator, the stall, when according to the FAA definition, is when the nose pitches uncontrollably or when the elevator reaches a stop. Every light airplane that I've seen in 50 years of doing this, it's when the elevator reaches the up stop. Yeah, you're going to get some buffet and the nose may start to drop. But if you keep coming back with the elevator, it won't until you hit the up stop. Like I say, every airplane that I've seen, that's the case. So, and a lot of times, you know, what you learn in pilot training really isn't a FAA definition stall, okay? It's essentially approach to the stall. It's, you know, first indication kind of thing, and then you recover. But it may turn out to be quite a difference. The other thing is that the FAA requires that you do the stall at the most unfavorable center of gravity at gross weight, at takeoff, max takeoff gross weight, or correct it to it. Now, normally when you're doing these things for real, we're not going to be over gross weight, okay? But if you were doing them for real, you would load the airplane above the takeoff gross weight and correct, so you're always correcting down. We won't do that here because we're not really doing this as part of an FAA test in an experimental airplane, okay? When you do this for certification, the airplane is in experimental category and the FAA allows you to overload it as much as 5%. And that way you can, you know, load it more than 5% above the maximum gross weight, go up and do these stalls and still be above the gross weight so all your corrections are down. In the course here, we'll have to correct up. The FAA does not, for performance, does not like to see corrections up. Okay, they prefer to see them down. So in performance, you're allowed plus 5% above the maximum gross weight or minus 1% That's the tolerance, okay, that they want you to be in when you do the test. Like I said, we won't be able to do that, but we'll get as close to the gross weight as we can, and you can see the procedure, and, you know, we'll correct them to gross weight. Okay. And we'll do them, like I say, power off. Trying to do zero thrust requires some calculations. It'll generally give you a knot or two lower stall speed, but it isn't hardly worth the work, okay, that you have to do to determine what zero thrust is. Because you have to be at a certain RPM at the time you do the stall. Well, you know, that requires here you're trying to adjust the RPM as you're going into the stall and that sort of thing. It just makes it much more difficult to do. But we'll do them clean and we'll do them flaps down. We'll do 3 of each. That way you have, what we will do is that we'll get numbers for 3 of them. We'll correct those to maximum gross weight. Each stall will correct it. So you'll need to get the weight. Okay, you'll need to get the speed, of course, and several other things. The FAA is interested, and rightly so, in stall warning. When you get the stall warning, if the stall warning is too high, after a while, people begin to say, you know, it's the cry wolf thing. You know, hey, you know, that's just normal. The airplane does that. Well, if it's too high, if it's too low, you don't have adequate warning, and you know you're in the stall before you know it. So the current rule gives you a bottom number, but it doesn't give you a top one. The older rule gives you said it should be no more than 10 knots nor less than 5 knots above the stall. So you had a rather small range that the stall warning had to go off in. So we'll record the stall warning and we'll record the stall itself. And so you may want to, as in your groups, work out who's going to get what number, because you may not be able to get both of them. Now the important one, of course, is stall, but stall warning is also important. So that's what we'll be doing next time. Generally, we'll go up and we won't be able to do all 6 of them at one time, in one, without climbing back up. So while we're climbing back up, we'll do one power on. The FAA does not require you to get stall speed numbers power on. They don't really care too much because they know there's too much variance in those kinds of numbers. The airplane will buck and jump and carry on before the nose ever pitches uncontrollably. And as a result, the airspeed indicator's kind of all over the place when that's going on. And so they're not really too concerned with that number. They know it's going to be lower than the power off case. So, but we'll do one just for your amazement. You know, the normal ones with power off, the nose isn't going to be too high before the airplane stalls. Power on, it's going to be way up here like this, you know. And so they're fun. You know, don't worry about stalls. A lot of folks are scared to death of them because their flight instructor was scared to death of them. You know, and the thing of it is, you know, people worry about the airplane spinning out of a stall. And that's what you have to do to make the airplane spin. You have to stall it. It won't spin when it's flying, okay? It'll do a very tight spiral. But you can tell a tight spiral versus a spin. But a spin, the airplane has to have a lot of side slip. Generally, to do a spin, yes, you stall the airplane and then you put in full rudder in the direction you want the airplane to spin. And you hold it in the spin, in the stall, and of course then does auto rotation, changes from an airplane to a helicopter. But it's, after a while, it's going straight down, and it's very fast, okay, about 6,000 feet a minute. The last airplane I jumped out of went from 10,500 feet to the surface, which was 200 feet in about a minute and a half. Okay, so they go down pretty quick. All right, any questions about what we're going to do? Any questions about what we did last time? You know, I said you could work together in reducing this data. I would like for each of you to generate a report. And what I want you to do at the end of the class is have a complete report, so you don't have to repeat the basic stuff every time, okay? I'd like to see the data when you turn it in. I'll try to grade that and get it back to you. And so you can put together, at the end of the class, you can put together the complete report on the Cherokee 6. Okay, any other questions? All right, the last time we talked about power, and we talked about propellers, and we said we had to, you know, we had a certain loss through that propeller of power, you know, so we have a propeller efficiency. But we're going to come up with some ways to avoid having to calculate propeller efficiency, because we really don't know very much what it is. So we come up with methods to be able to determine how much power you're getting out of the engine in flight when you do cruise and climb and that sort of thing. But the first thing today, we're going to talk about jet engines and the measurement of thrust in flight. Again, much like power, one of the more difficult things we have to do in flight test is measure either power or thrust. If we only need pilot handbook data, then thrust measurement may not be necessary. We may be able to just put it as something that some thrust reference that the pilot has in front of him, like engine speed or that sort of thing. Our fuel flow, of course, you know, where's all the energy coming from this? Coming out of the fuel, right? I mean, that's one way, even for propeller-driven airplane, you can measure. If you can measure the fuel flow real accurately, you can calculate and you have some idea what the efficiency of the engine is, you can calculate what kind of power you're developing. Complicated though, and your instrumentation has to be very good. But we always question whether the engine is developing the standard thrust for a given fuel flow. One of the things that the military does, and it's, to be real honest with you, it's kind of crazy and cost us as taxpayers a lot of money, because they buy an engine from this guy and an airplane from this guy, and they put the two together. And then you have this contest. Well, your damn engine doesn't produce the thrust. Oh, it's your stupid airplane. It's got too much drag. And that's the argument. As a result, the Air Force has built a big wind tunnel complex in Tennessee called Arnold Center, where they go to great lengths to determine what the thrust is. So they've got wind tunnels that are bigger than this room that are capable of Mach 2.5. Now think about that. You take a wind tunnel bigger than this room, 16-foot square test section, and run it at Mach 2.5. it requires all of the excess energy that the Tennessee Valley Authority can generate. And they only run it between midnight and 6 o'clock in the morning because of that.
Not cheap.
It's not cheap, not cheap. But it's all because they buy, instead of just going to Boeing or Northrop Grumman or whoever and saying, I want an airplane that does this, and you get the engine. Instead, they go to General Electric or Pratt & Whitney and they buy the engines, and then they mount them to the airplane, and then the Air Force is the guy responsible kind of in the middle to making sure that both of them do what they're supposed to do. Now, if you go down to Piper, you go to Piper and buy an airplane, you buy it from Piper. You don't buy the engine from Lycoming. Piper buys it from Lycoming. And then Piper is the response, if it doesn't do what Piper says it does, then you go back to Piper. You don't go to Lycoming and say, oh, your stupid engine don't produce the power it's supposed to. So sometimes we do very strange things, and the engine stuff is, engine and airframe separately is one of them. So, we want to find out about this, and so we find ourselves trying to measure thrust. Now, I'll have to admit, the aero guys are one of the, if you go to a company and you work in aerodynamics, you always want to know if your drag estimates are good. And you'll really never find out. Okay? Because of this difference. Okay? You'll never find out because the thrust and drag are so intertwined that, which is it? Are we down on thrust or are we up on drag? Who knows? All right, well, jet engine produces thrust, takes the mass of air in the intake, squirts in some fuel, adding energy, and accelerates it out the tailpipe. Pretty simple idea. We talked last time about the turbocharger and about how the turbocharger had a compressor on the front and it took engine exhaust and turned the turbine that drove the compressor. Well, all that happened with the jet engine was they stretched that thing, put some burner cans in the middle, squirted fuel in, and did away with the reciprocating part. That's essentially what a jet engine does. Well, gross thrust, that's all the thrust coming out of the tailpipe, and you're going to find that before long we're going to come up with this term ram drag. Okay, and we're going to try to determine net thrust. But anyway, the gross thrust is the mass flow, the velocity at the exit, plus the area of the exit, pressure at the exit, and the ambient pressure. Okay, that's the gross thrust. But that does not consider the forward motion of the airplane. Essentially, with a jet engine, the faster you go, the faster you go. Okay, because you cram more, the more air you can flow through that engine, the more thrust it produces. But the air coming into the inlet creates some drag, and we call that ram drag, and it's just the mass flow and the true airspeed, okay, in simple terms. However, when you get into it, it's not quite so simple. So the net thrust produced is expressed as the gross thrust minus the ram drag. And if we assume that the mass flow in the engine is equal to the mass flow out, so here's the mass flow out, mass flow in, then the net thrust can be expressed by that equation. And it's a reasonable assumption if we remember that the mass of fuel is small when compared to the mass of air going through the engine. We don't put a lot of fuel in compared to the mass of air that goes through a jet engine. Now, some jet engines, when you see the fuel lines, you know, J79 fuel line is about that big around going into the engine. There's a lot of fuel going in there, but not near as much as the amount of air going through that thing. So we kind of make that assumption, and that helps us a bit. And we have to consider what's going on in the exhaust nozzle. And we can have two cases there. The flow can be either subsonic, which we call unchoked. If you hear that term, that means subsonic flow in the exhaust nozzle, okay. Or sonic, which we call choked. What it means is there's a normal shock wave standing in the nozzle. And for subsonic flow, or the unchoked flow as it's called, the static pressure in the nozzle is equal to the ambient. Okay, so it's just the pressure at the exit over the ambient pressure is equal to 1. And the temperature in this nozzle is related by the equation. Again, this is total temperature on top, temperature at the exit. Pressure, total pressure over ambient pressure. Gamma, in this case, is escape me, gamma is essentially 1.4, okay, it's the
ratio of specific heats.
Specific heats, yeah, ratio of specific heats for at elevated temperatures. 1.4, 1.3, something someplace in that thing. I think 1.33 they usually use for elevated temperatures. The velocity at the nozzle for the unchoked case is defined by this equation. And again, gamma here is this, and you know, we find that a little later on in this course I'm going to use gamma for flight path angle. Okay, but in this case it's the ratio of specific heats. Okay. As I said, in engineering, you know, we run out of Greek letters and regular alphabet. And so we end up using them over again, which really confuses us. You know, engineering would be a lot simpler if we knew that gamma meant just this, right? Be a lot simpler. But, you know, we're stuck with it. Now, if we assume that the inlet and the exit mass flow are equal, and that, you know, that's an assumption, like I say, that isn't quite true because we're adding that fuel, but you know, it's not a bad assumption. Then the mass flow is the area of the nozzle, the velocity at the nozzle, pressure at the nozzle, you know, gas constant times temperature. And then if we substitute that into the first equation, then we come up with this term for an unchoked engine. The gross thrust over the area of the nozzle is equal to 2 times the ratio of specific heats over the ratio of specific heat minus 1 times the ambient pressure, total pressure over ambient pressure. And that tells us something about measuring thrust. You put a probe in the nozzle, and we have an ambient pressure source through, say, our static probe. Static pressure, you know, that's really pretty as close as we can get on the airplane to this, right? we know we calibrated it last time. Total pressure over ambient, so we can measure a pressure ratio. And if we know the pressure ratio, you look at this, all these other things are constants. Area is known, so we can determine the gross thrust by sticking a probe in the tailpipe. And by introducing the pressure ratio, delta, you know, that's the atmospheric pressure ratio, the same thing you're going to, have to correct in what you did last week, The reason we set the altimeter at 2992 is so we're reading the pressure altitude, right? Okay, so then we take that, and from that, we can do it. So, and we know the pressure here, we put delta in here, so we've got delta times the area of the exit. Knowing what our altitude is, we'll know what delta is. Pressure at sea level, that's a constant. And so, here we are. We're measuring the total versus the ambient. And again, this is 1.33 or something like that, so we can